to GeoHug. So before we kick off today's session, I'd just like to take this time to acknowledge the traditional lands which we're all coming from today. I'm here on the beautiful lands of the Gadigal of the people of the Aurora Nation, and I'd like to pay my respects to the elders past, present and future. So I am so happy to have Louise Corriveau joining us today. So Louise is a research scientist at the Geological Survey of Canada and an adjunct professor at the INRS in Quebec. So Louise is an expert at finding prospectivity clues in the field geology record of metasomatic mineral systems and high-grade metamorphic terrains. And she'll be chatting with us today about IOCGs, IOAs, and primary critical mineral deposits in metasomatic iron and alkali-calcic systems. Did I get all of that right? Because that was like a very big lot of geology words. Anyway. But yes, it's going to be a great session. So please use the chat. We'll be opening up the floor for discussion at the end. And yes, thank you so much, Louise, for joining. It's just wonderful having you.
I titled the talk In Each Other's Footsteps because, as you can see from the list of co-authors, we have a few Canadians, Louise Corriveau, Eric Potter, Randy Enkin from the Geological Survey of Canada, Jean-François Montreuil from McDonald Mines Exploration. We have a colleague from BRGM in France, Olivier Blain, as well as Australian, the famous Cathy Eric from BHP Olympic Dam, Adrian Fabris from Geological Survey of South Australia, and Vladimir Lizitsin from the Geological Survey of Queensland. In each other's footsteps, because we will be using our case studies from the Great Bear Magmatic Zone in Canada and other Canadian settings, because they are extremely well exposed. You have to imagine that the rocks have been glaciated, they have been cleaned, they are non-weathered or just a few micron weathering, just enough to make all the minerals stand out very clearly what they are. So we can see all the processes that have gone through the rocks through time, and we can see it in 3D, not only because of the relief, but also because there was amazing structural tilting or differential exhumation. So if you want to know what the systems look like from at least 3 kilometer depths towards surface, towards the epithermal cap, we've got it all. Now, you in Australia, you have the mining district, the supergiant deposits. So it's kind of nice to compare all our prospects, the undeveloped deposits with all the mines and deposits you have in Australia. Of course, critical metals are extremely important. We have our Canadian list, and if we look at the metasomatic iron and alkali-calcic systems, they are foundation for critical metal wealth, for precious metal wealth, because they're forming a whole variety of deposit types. Iron oxide-apatite deposit with iron, rare earth or nickel ore, iron oxide copper gold deposit with their uranium and as well some rare earths and PGEs. There's also iron-rich gold, cobalt, bismuth. So primary critical metal deposits, albitite also uranium, gold, cobalt, copper, molybdenum, radium. You can have skarn with iron, lead, zinc, tungsten, 5-element veins, epithermal, mineralization, and many others. Collectively, they have, in terms of resources, 12 critical metals. They have 8 additional potential byproducts. There are enrichment in many other elements, and there's primary resources in silver, gold, iron, phosphorus, lead, and rhenium. So very rich metasomatic systems. In Canada, we have done a lot of mapping, first of the Great Bear Magmatic Zone, and which is in northern Canada, and you have the map here on the right, with all the mineral systems that we have gone. This allows us to map the evolution of those systems, to map the linkages between the various alteration types and the mineralization types. And if we have any question that cannot be answered to one, we're going to find the same thing elsewhere, and we can constrain all the evolution of those systems collectively and also separately. In Australia, you have amazing public geoscience. You have put a lot of money into public research, into academic research, into regional gravity, magnetic, magnetotelluric surveys. Industry has been very innovative. They have conducted a lot of exploration. There has been a lot of investment. We have tons of discoveries and mining. So we complement each other. And of course, everybody is welcome to come and explore Canada because we have the deposits, we have the resources, and those resources are on tap since we have no mines. Now, you have heard me say metasomatic, iron and alkali-calcic mineral system. I didn't say IOCG system. Why? Because IOCG are a deposit type. The systems themselves form a whole variety of deposits. So we really focus on the fact that those are metasomatic systems. They are iron-rich, they have a lot of alkalis, they have a lot of calcic minerals, and the iron can be in the form of iron oxide, but it can also be iron silicate, iron sulfides, and iron carbonates. And your Cloncurry district is a very good example of that whole variation. Our global comparison, here are the case studies that we have collectively studied and published about in the special paper 52 of the Geological Association of Canada, as well as with our USGS colleague. We had a special issue of economic geology in 2016. So we have a lot of deposit case example that we have been able to compare and study going into the field, or if we didn't go into the field, having collaborators who have worked there extensively. In addition, companies are giving us a lot of proprietary data that has been unpublished. Let's just think about BHP Olympic Dam, who have provided us with 20,000 analysis and rock physical property. But the same thing for the government surveys, GSC, GSSA, USGS, GSQ have very extensive data set that we draw upon. Canadian industry have been fantastic in sharing their unpublished data as well. So what is the result of our work? Well, this is really a recap of what we are finding. The bottom part, the ascending fluid plume that somehow collects at the mid to upper crust interface and that starts rising towards surface, we haven't seen. The rest of the diagram, we have mapped repeatedly. So it's no speculation. And what we have done is group all our mineral assemblage into alteration facies. So a bit like metamorphic facies. I'm a regional field geologist who specialize in metamorphic terrains. So I've used the approach of metamorphic petrology, take mineral assemblage, group them. As soon as they kind of act together, they form in the same physical-chemical condition, we regroup them, and then we look at the timeline that the cross-cutting relationship among them, or overprinting, or the distribution from depth to surface is telling us how the system has evolved. So the fluid plume arrives, and it starts first by making huge albitite corridor. So now here at the bottom in one to the lower left of our diagram, then we have the albitite corridor. The albitite is not simply albitization of a sedimentary package where it's very easy to albitize feldspar. No, we're talking about any rock type or nearly any rock type totally transformed into albitite corridor that can be 500-meter wide or 1 kilometer wide by 10-kilometer long at least, or even 30-kilometer long, or even longer in Australia. Now, as you're doing your albitite, if you have carbonate rocks, you will be forming skarn. Now, the second alteration species that you will form as a physical-chemical condition of your fluid plume evolves is a mineral assemblage suites with amphibole, magnetite, apatite, and sometimes epidote. Their diagnostic cation is calcium and iron, and the metamorphic petrology may kind of link those amphibole mineral assemblage to what you would find in the high temperature amphibolite facies in metamorphism. So when you see those mineral assemblage, for metamorphic petrologists, it's really easy. You at high temperature. Then you can compare that to green schist facies mineral assemblage, which will be the lower temperature, and we'll come to that later on. So we've done the high temperature calcium iron alteration facies. If we are on sedimentary rocks, the next facies will be amphibole, biotite, K-feldspar, and magnetite, giving you a high temperature calcium, potassium, iron alteration facies. And then we come to the very typical iron oxide breccia, where you get magnetite, biotite, and K-feldspar. Moving on towards the low temperature potassic iron alteration facies, where you would have cerussite, hematite, and in between you often find K-feldspar breccia or potassic skarns. The low temperature potassic iron alteration with hematite and cerussite also has counterparts rich in epidote, in carbonates, or in chloride, and we label those as low temperature calcium, magnesium, iron alteration facies, acknowledging that really it gets extremely varied at low temperature. And then anything that could not precipitate beforehand then has to precipitate towards surface. So you form high zones of silicification. You can form epithermal caps with very rich in cerussite, argillic alteration, advanced argillic alteration. You can precipitate all your CO2 in the form of carbonates, barium and fluorine, and all sorts of things. The same way as cations are coupled and decoupled as the systems evolve, so will metals. Albitite, they precipitate, it's just a leaching zone, so it's just barren during primary crystallization. The skarns can evolve to to iron skarn, they can be tungsten skarn. And after that, you're going to form at the high temperature calcium iron alteration facies, you're going to form the iron oxide-apatite deposits. They can be very rich in rare earths, including heavy rare earths, and nickel and other elements. In sedimentary rocks, this is where you're starting to precipitate your cobalt in a big way, as well as bismuth, as well as gold. At the potassic iron oxide breccia with magnetite, if you have more biotite-rich assemblage, then you may still precipitate a lot of cobalt. But if you have biotite, K-feldspar in iron oxide breccia, that's when you start precipitating a lot of copper, as well as your gold and your silver. Potassic skarn, they can have lead and zinc, and copper, and the low temperature potassic iron that will make your hematite group IOCG deposits. Then you'll be getting your gold, your silver, your copper, your uranium, your light rare earth. Molybdenum will start precipitating, and it will continue towards the end as well. At the end, epithermal cap, 5-element veins, tons of other different type of veins. As well, at that stage, any events that occur after you've done your primary metasomatic systems. Any events will remobilize metals and will form new sets of veins. So that you have to be extremely aware of that, because if you date any veins, then you can have nearly any age for your mineralization, and it gives you a lot more information about any magmatic or tectonic events that allowed fluid circulation at that time than the primary mineral systems. And I'll come back to that later. So the best way to deal with those systems is to see them as a chain reaction. It's a bit like uranium going to lead. If your uranium decay, you've lost control of your system, it's going to end up in lead. Those huge hypersaline fluid plumes are so reactive. They are so out of disequilibrium with normal host rocks that they will trigger a chain reaction. The fluids interact with the host rock. First, it will make the albitite corridor leach everything that is not stable in albite. Any elements that is not stable in the rock will be moved to the fluid plume. Fluid plume will change its physical-chemical condition, will precipitate the high-temperature calcium iron alteration. The high-temperature calcium iron alteration, anything that is potassium, magnesium, anything that is not calcium and iron will be transferred to the fluid plume, and so on and so on. So you have here the relative timeline of those alteration phases. You have case example of the various alteration assemblage that you may find at each phases, and each phases can form replacement, vein, or be brecciated. Albitite, any host rock nearly will be transformed into massive albitite. Often they will be white at first, and then they will transition to pink albitite. The albitite will go along damage zone. It will form halos along veins. It will coalesce and end up with pervasive albitization. It leaves a very porous rock. And because it's so porous and because it's often formed along fault zone, then it tends to brecciate. It's very common to end up with albitite breccia that are very extensive. Once you form your albitite, this is a porphyritic andesite that is albitized and then transformed into albitite. Then you will evolve to, or you have the albitite cross-cut by high-temperature calcium iron with amphibole biotite. And in the transition, you may have amphibole with albite halos as you're transforming from transitioning from just Na to the CF. If you have skarns, they'll get amphibole altered. And the high temperature calcium iron alteration is often amphibole dominant at first, and then it transitions to magnetite dominant at first. This outcrop is exactly the same location as this outcrop. And here you have the white albitite that has evolved to pink albitite, and that is then replaced by amphibole. So when you see something like that, first you have a heart attack. Second, then you split things into the little piece that they have to be fit in. So you have the albitite that is brecciated, where the sedimentary rocks was interlayered with more carbonaceous layers. Then you have skarn, stratabone skarn interlayered with stratabone albitite. And then the next alteration species is the amphibole magnetite alteration species that is cross-cutting everything, but also going down as stratabone alteration, just replacing the early skarn and some of the albitite. So you take each of the stages put it in the correct alteration facies, and move on to your next outcrop. The high temperature calcium iron alteration is great at fooling people. If you have beautiful stratabound magnetite alteration, then it can really resemble a banded iron formation. But look at that. To the left, we're starting to boudinage the rocks. On the same outcrop, the amphibole and the magnetite altered sedimentary rocks is now folded. But the beauty of the Great Bear is that there's absolutely no post-tectonic event. All that deformation is taking place during metasomatism. It has nothing to do with an overprinting orogenesis. So when you see something like that, you don't jump to the conclusion, oh, those must be old rocks because they are all deformed. No, they were deformed during metasomatism. The same alteration facies can form just beautiful brittle breccia. The magnetite alteration can be very selective and prefer to altered class and less altered the matrix. If you're at El Laco, then you're starting to alter the andesite breccia, and then you completely alter it. Just beautiful stuff. Magnetite vein can have magnetite-rich halos and carbonates. Magnetite can crystallize with apatite and then be fluidized in breccia, such as this beautiful fluidized iron oxide-apatite breccia that cross-cut in albitite, or it can go to apatite infill with very minor amphibole at some of the margin of the breccia. So really, the high temperature calcium iron alteration can be amphibole dominant, magnetite dominant, it can be apatite dominant, and very locally, it can be epidote dominant. This is where you're going to start precipitating a lot of rare earths, especially in iron oxide-apatite mineralization, where the system was able to evolve to potassic and potassic iron alteration. If you don't have the potassic alteration in your system, you're very unlikely to have rare earths. Now, this is going to bring you to 2,500 ppm rare earths quite often, but you'll be able to remobilize those rare earths and make rare earth deposits. Next alteration is the amphibole biotite high temperature calcium iron alteration facies. This, at the extreme, will lead you to iron-rich gold, cobalt, bismuth, plus or minus copper, because really the copper will precipitate at the biotite-rich potassic iron alteration and the K-feldspar-rich potassic iron alteration. Now, look at this amphibole vein, which is high temperature calcium iron alteration facies, cross-cutting what should come later. Well, how do we do that? At the Nico deposit, where those case examples are from, there's a lot of magma being in place coevally with metasomatism. So each time you add magma, you increase the temperature of your fluid plume. So if high temperature calcium iron potassium alteration facies were stable and you increase the temperature, then you switch back to the high temperature calcium iron, so amphibole only veins. And you can play yo-yo with systems like that quite a lot. So we have done a lot of alteration facies mapping. The sum of alteration is giving us our metasomatic system. We have facies, timeline, or deposit type mineral systems. And just a take-home message, the relative timing we've mapped repeatedly. The Mayock framework I gave you originally is map, it's not speculation, but you will need to adapt it because if you have more magma being in place, if you can tap a lot of low temperature fluids, you can play yo-yo with your system. We've seen host rock be totally transformed into new rock type, which means we've seen host rock having chemical composition totally change. Now, if you change minerals, you're not only changing geochemistry, you're going to change rock physical properties. And we will look at global comparison. So this is the next series of slides that we're going to see. And mineral chemistry change as alteration facies change, but I'm not going to talk about that for this talk. So let's go back to the Great Bear. We have a beautiful 2-kilometer thick andesite sequence. It's all porphyritic andesite. It's so simple. So let's have fun with it. We totally transform it into albitite. Then we have a gorgeous pygmatoid amphibole magnetite albite that I'm not showing here. Then you move on to K-feldspar altered andesite, hematite altered volcanic matrix. And you see the plagioclase phenocrysts here. They are here totally replaced by silica, by quartz. And that same unit gets nearly all hematite. What does it mean in terms of change in composition? We start with the andesite. Then we move on with the albitite, significantly enriching the sodium, but removing all the other elements. There's relative enrichment in silica and aluminum. We increase the potassium significantly at the K-feldspar altered unit. We keep about the same kind of aluminum as the host andesite. Then when we go to the hematite quartz, we keep the silica. The silica goes to replace the phenocryst, and the matrix is all being transformed into hematite. Iron is really increasing, the other elements are really decreasing, and aluminum is starting to go. And when you are only hematite, aluminum is gone. Don't worry, the epithermal cap is just waiting for your aluminum, so it's not lost, it's just going up. So how do we portray all that? Well, it's very simple. With molar proportion of sodium, calcium, iron, potassium, and magnesium. A normal andesite will have nearly an equal proportion of those elements. This is a calcaline suite going from a basalt to a rhyolite. Note how much there is little difference to what is going to come as metasomatic output. This is a short-shronitic suite, still 3 to 4 cation dominant. This is shale suite. So when you transform an andesite into albitite, you get rid of all that component of the host rock and you replace it by sodium. That means that all the elements that were there before and that occupy that proportion is now all gone to the fluid. All the metals that are not stable in there is gone back to your fluid as well. So you do that, and here is the change of chemistry for each alteration species. And here are some case examples of deposits that occur at each of the facies. To portray that, we have a discriminant diagram where we don't only plot dots, but we really use the barcodes to be able to distinguish when you have least altered being altered, or let's say albitite being overprinted, and all the diagrams can be covered going back and forth between least altered to most altered being overprinted. So barcodes, when you get used to them, you can really easily distinguish what is a host rock that has been albitized from a host rock where you have add an overprint to it. The most altered rocks will follow this path on the diagram, but if you take all your data set, it will cover the diagram. So let's have a look at what we do in terms of metals. We go from the albitite to the high temperature calcium iron. We make an iron oxide-apatite deposits. That deposits evolve to potassic alteration. It's loaded with rare earths. And because it was the rare earths were remobilized, we achieve very high rare earth contents. Heavy rare earth reaching above 1%, and so does the light rare earth. On the rock contract diagram, you can see that those deposits can be very rich in heavy rare earths as well as in light rare earths, even more than the carbonatites that are being mined. If we go back to the Great Bear, in the northern part of the Great Bear, the First Nation, the Dene First Nation, are exploring the Kamsol River district, and they have iron oxide mineralization that evolved to IOCG mineralization. You have a lot of potassic iron alteration species as well as your iron oxide-apatite mineralization, and they have a fair amount of rare earths. And if you plot the barcodes and the contents, you can really see how the metals are coupled and decoupled depending on your alteration species. Normal alteration species will increase in rare earths when you are at the high temperature calcium iron. Iron oxide-apatite are even richer, and if you recrystallize those rocks, you can really enrich their rare earth contents, as we see it in the iron oxide apatite deposit of Josette in Quebec. At the Nico deposit, we go from the siltstone to albitite to high temperature calcium iron, amphibole to magnetite dominant, and then we start precipitating cobalt with arsenopyrite, cobaltite, as well as bismuthinite and gold. This evolved to biotite-rich copper zones, and as well as to bona fide iron oxide copper gold deposits that prospects, sorry. And we have also a huge albitite corridor that is totally decoupled from Nico. We find it by climbing a huge hill, going back down a huge hill, and arriving to a 3-kilometer long albitite corridor that will be mapped as hornfels. So that's very important that if you have one alteration species, to go and look for all the others and provide a framework for your entire system, because the albitite corridor is loaded with uranium mineralization that is totally decoupled from the Nico deposit. So if we take the barcodes and plot their content in gold, indium, bismuth, tungsten, cobalt, we can see the barcodes are green and black and a little bit of pink. So high temperature calcium, iron, and potassium. The copper is pink and red, red and black, potassic iron alteration species. So you can really see how the elements are coupled and decoupled according to the alteration species. Nico reserves fits here in the Slack et al. Diagram. Blackbird resources is higher. The historic cobalt value of OD is lower, and Nico is highly underexplored still. So really, where does it really fit along this line will be to a lot of mineral exploration and mining to decipher. We can find also a lot of cobalt at the KFE alteration species that is rich in biotite, such as the mill deposit in US. So the uranium, look at that. The uranium at Nico is here. it's below continental crust values, while the uranium is all moved to the albitite corridors and is associated with potassic iron alteration species. You have the same thing in the Cloncurry district. Your albitite breccia being cross-cut by amphibole, then magnetite biotite, infilling albitite breccia at Ernest Henry, and evolving to your iron oxide breccia and then to your carbonate units. So if you take the framework, then you can fit everything beautifully in the Ernest Henry deposit. If you take the IOCG diagram and with its barcodes, that's picks from the Cloncurry district. You go from your albitite, high temperature calcium iron, to your very rich iron oxide zones, and then to the potassic iron alteration. And that's Ernest Henry per se to the right. Now, if we continue the system, we end up with the low temperature potassic iron alteration. And we are here at Olympic Dam, where we start with the granite, we increase K-feldspar alteration, silicization with hematite to the point of having just hematite and then hematite quartz. But beforehand and deeper, we have crystallized quite a lot of magnetite, magnetite with apatite, magnetite with chalcopyrite. And if you plot the barcodes in the region, you do have sodic components, so you have everything at Olympic Dam as well. Now, continental crust values, look at how much endowed Olympic Dam is. There's so much enrichment, it's just unreal. That's the IOCG diagram, and we can come back to that during the question period if you wish. And again, all that is published recently in the special paper 52 of the Geological Association of Canada. Now, if you are at Punt Hill, then you have skarns that are K-feldspar altered, and they have also low temperature calcium magnesium iron alteration, a lot of chloritization, and this is where you're precipitating your sulfides, copper, and zinc. If we go back to Cloncurry, you're getting your cobalt in the potassic iron, potassic alteration species, and calcium potassium iron alteration. Olympic Dam, the cobalt gets more enriched in the iron oxide rich component of the deposit. And then at the Nico deposit, we are in the potassic iron, calcium potassic iron and potassic iron alteration species. Same thing for Blackbird. But look at how much cobalt we end up having in those gold, cobalt, bismuth, iron-rich deposits. They can be iron oxide-rich, they can be iron silicate-rich. So really, if you want cobalt, you may prefer those that are not bona fide IOCGs. And that's the important part of understanding the systems, is that depending on what you want to find, is you have the alteration species that will tell you where to look for. So you want heavy rare earth? Well, why don't you look for iron oxide-apatite deposits in systems that have evolved to potassic iron? You prefer light rare earth? Olympic Dam is the right place. It's good for gold as well. You prefer bismuth and cobalt? Well, maybe you will be choosing the gold, cobalt, bismuth deposit types. Each alteration species will tell you where to look for. So we have our systems that evolve. Let's not forget that you can have iron oxide, but you're starting to develop very similar things if you have iron carbonate, iron silicate, or iron sulfides. And you also, your systems will evolve to iron poor components as well as your epithermal cap, 5-element veins, and all sorts of veins. The same way that the high temperature calcium iron was able to have only amphibole, to only magnetite, to only apatite, then your system can lead to just a molybdenum rhenium deposits, or it can lead to anything. We don't know what it's capable of doing. We just know it's capable of doing anything. So rock physical property, let's go to that briefly. Magnetic susceptibility versus bulk density. Olympic Dam, 10,000 analysis just for an Olympic Dam. We haven't processed the 10,000 others from the region. Great Bear, well, I apologize. We have gorgeous hematite breccia, but I forgot to send some for analysis of rock physical property. But in any case, post-granite Olympic Dam, the mafic rocks, the scounts in the Great Bear, now the albitites somewhere in here. So now let's look at the critical metal contents of other metals. Iron, of course, is very simple. It goes where the magnetite and the hematite is. Cobalt, yes, it does go where iron and is, but it really expands to other area as well. Light rare earth, it much prefer the hematite at Olympic Dam, but look at the light rare earths is different in the Great Bear. So there's plenty to look for. And we have done that for all the elements, but I'll spare you the rest. So now we have the model and we can fit what we observe against the framework. Now, for a long time, with all due respect to BHP, you know, it was very hard for me to understand what was going on at Oak Dam East because, well, I look at Davidson and they have all this part and then they have the other part. So I mean, if you have that part and you have the other part, then you have to have something in between. It just, those systems are evolving systems. They cannot just stop and disappear if they've managed to go to the end as spectacularly as some of the Oak Dam East had. So I'm very glad to see that, yes, Oak Dam is very well behaved with the discovery of Oak Dam West. So that kind of logic you can apply to everything. Nico, we've applied it. When I went to Nico, some people were saying it's just a scar. Well, let's test it. I mean, if it's just a scar, it won't have an albitite corridor next door to it. So we climbed the hill, climbed down the hill, find the 3-kilometer long albitite corridor. Well, that solved that problem, especially that it has hematite breccia, it has bona fide IOCGs on top of it and within it. So Nico is not just a scar. Nico is an high temperature calcium potassic iron alteration species that has gold, cobalt, and bismuth ore. And the system can also have IOCGs that needs to be discovered. When I was in Candelaria, next to Candelaria was a small mine. And as I was sitting on the waste pile, I just couldn't believe it. Those were my rocks. They were the Nico rocks. I turned to the left and there's the mine tailings of Candelaria. So when I'm at Nico, what do I ask myself is, where is Candelaria? Maybe it doesn't exist, but maybe we still need to look for it. So Canada has fantastic deposit types. They are all undeveloped. Some of them, such as Nico, have a partnership agreement with the First Nation. In the northern part of the Great Bear, the Dene First Nation are the ones who are exploring for gold, silver, cobalt, bismuth, rare earths, and all the other elements. So it's the same thing for all our systems. They are all underexplored and they are all very promising. And I'm hoping that some of you will come and play in our playground. If you do so, you can count on fantastic field geology, but important not to map albitite as cyanide, albitite as silicification, high temperature calcium iron alteration that is amphibole dominant. Don't map it as amphibolite, and don't map the stratabound magnetite as iron formation. Of course, if I'm showing you those pictures, there's plenty of examples where this has been misinterpreted, and I'm afraid to say that I have a few silicification zones that I have to get rid of and replace by albitite. So everything that I've discussed, you can go and buy for very cheap, or Geological Association of Canada Spatial Paper 52, Australian are publishing in it, Adrian Fabris, Les Catona, Anthony Reed, Kathy Ehrig, Roger Skiro. We have Chinese colleagues, we have Canadian colleagues, and so there's plenty to look for. So, Mazi, merci, thank you. And let's not forget that we have gorgeous setting, but they do have infrastructure, and we're looking forward to seeing you in Canada. Thank you.